You all studied during spring break, right? Okay, so let's kind of remember. Let's try to remember a little bit about talk. I know it's not easy, but I think with effort we can do it. Okay, so we were talking about the reactivity of carbonyl compounds and esters. And I think where we left off was Grignard addition or alkyl lithium addition to an ester. And what happens is shown, I mean, it kind of makes sense, right? You have the methyl nucleophile, remember that Grignards and alkyl lithium act like carbon nucleophiles, adds to the carbonyl, forms this tetrahedral intermediate, and this tetrahedral intermediate has ethoxy group attached, so you can lose ethoxy group to give you a ketone. Now, to compare the intermediate product and the starting material is an ester, intermediate product is a ketone. Which is more reactive, ester or ketone? Well, you know that ketones more reactive than esters because it goes from acid chloride and hydride, aldehyde, ketone, ester, right? The reactivity series. And so the next addition takes place even faster than the first. And so methyl minus attacks that carbonyl. And you end up with a tertiary alcohol, but not just any old tertiary alcohol. The tertiary alcohol where two of the groups are identical. Okay, so if you ever want to generate a tertiary alcohol with two groups the same, this is the way to do it. It's just easier because you do it in one step. And so the key though is to recognize that the carbonyl group of the ester is electrophilic, right? It's got a partial positive charge, so nucleophiles attack there. Now, if I had something more reactive than an ester, then like an acid chloride, then that's going to work just as well, right? I mean, this is also extremely reactive, much more reactive than ester. Nucleophilic addition will take place. Now the leaving group is chloride, not ethoxide, even faster to get to the ketone. And once you have the ketone, of course, it's going to keep going to the tertiary alcohol. Well, let's just say that I want to stop right there. Well, how do I do that? Let's talk about how you can't do it. You can't do it with a Grignard, can't do it now for lithium, because you already know that if I have the alkyl lithium or the Grignard, what's going to happen is I'm going to end up getting the tertiary alcohol. So what I have to use is I have to attenuate or lower the reactivity of the nucleophile. And the way you do that is you make the cuprate, something we've seen in the past. So you start out with, say, 2 methyl lithiums and 1 equivalent of copper 1 iodide. Copper, by the way, has 3 stable oxidation states, 0, 1, and 2. And so you can purchase or you can prepare cuprous salts, that's copper 1, or cupric salts, that's copper 2. So cupric iodide would be copper plus 2, that would be copper I2. This is copper 1. This gives you this weird reagent where you have 2 metals. And the first time you see this, you say, gee, how can this, this looks kind of weird, doesn't it? Because look what you've got here. You've got copper with a methyl group and another methyl group, a minus charge on copper, that has the cuprate, and then you have lithium plus. Well, okay, so we know that copper is a metal, it's electropositive compared to carbon, so this is a formal charge, but hey, you know that negative charge is probably sitting on these 2 more electronegative carbon atoms, not on that electropositive copper. But these are very strange reagents. They don't react like Grignards. They do chemistry that you just can't do with any kind of Grignard. And so one of the things they can do is they can react with acid chlorides to transfer only one of the R groups. Now you end up losing the other one, so you end up throwing away the other R group. There are ways around that, but we don't. That's not for this class. But you can in fact form the ketones from the acid chlorides using the cuprate. Cuprates do other things. We're going to see those again, but they do not react with ketones. They will, and this is kind of an aside, if you let them, they will react with an aldehyde, but that reaction is also slow. So you can usually The reaction with the acid chloride, you do that in the presence of an aldehyde, it's not a problem. Okay, so now let's shift gears just a little bit and talk about something very practical, and that is condensation polymers. Now, polymers, we've seen these before. We've seen polymers before. So what's a polymer? Polymer is a really, really big organic molecule that has a repeating structure. Okay? So in other words, I take X, organic molecule X, and somehow I make a molecule that's X, and so on. Something long and linear. Sometimes they don't have to be linear, they can be three-dimensional too, but it's a very large molecule that is formed of identical pieces. And so you can start with adipic acid, this is dicarboxylic acid, and then through the amide, make the amide, you dehydrate it, you end up with the adiponitrile. That's the corresponding dinitrile. Now, we know that carbon-nitrogen bonds can be reduced. We could have done this with lithium aluminum hydride, but you know, on an industrial large scale, lithium aluminum hydride is never going to be practical because of the hazards and also just because of the workup. It's much easier just to do a catalytic hydrogenation. Think of it. You take the adiponitrile, you put it in a vessel, pressure vessel, pressurize it with hydrogen catalyst, and then at the end of the reaction, just filter off the catalyst, and there it is. No aqueous workup, no nothing. And so that gives you this compound, hexamethylene diamine. Diamine, and then 6 methylene groups in between. Now you take these two, you condense them. And so you take the adipic acid, the hexamethylene diamine, and the first thing that happens is an acid-base reaction, right? And then if you heat the heck out of these, it'll spit off water and will form a condensation polymer, which is known as nylon 6,6. And so you end up with a long polyamide. This is, a very good example of condensation polymer. So that tells you that you can make amides kind of in a different way, right? You just no acid catalyst or anything, just heat it up. And so this of course generates water, and the water has to be removed from the reaction mixture. Now, addition polymers we've seen before a long time ago with the polymerization of ethylene. Polyesters are also condensation polymers. So you take terephthalic acid and ethylene glycol, and by heating, you just split off water, and you end up with polyester, which is this stuff here, and that's what's used to spin fibers for leisure suits or whatever. So you guys are too young. You don't know what leisure is. It's a joke. Yeah, it was kind of a, I don't know if back in the, I guess, 70s, early 80s, it was a really kind of ugly fashion trend. Anyway. So ethylene glycol, terephthalic acid, you get polymers. And there are many other polymers that differ just a little bit. Kevlar is one. I think there's a problem in your text that asks you to think about Kevlar. Kevlar is, of course, the stuff, that's a polyamide. That's the stuff that they use to make a bulletproof vests out of and many other articles. Waxes are esters, right? And if you have a long linear carboxylic acid, a long linear alcohol, and you form the ester, that's a wax. So this particular one is carnauba wax, which is derived from some kind of Brazilian palm tree, and it's used for car wax. It's hard and brittle and whatever. Now, one thing I want to point out to you guys, take a look at, okay, so this is glycerol stearate. Stearic acid is the stuff we get from, this is beef fat, okay? So when you eat a steak, that nice mouthfeel that you get, yummy, it's from this stuff here. So in food, you really like we're genetically programmed to love this stuff. Now, what I want you to notice, two things I want you to notice. Take a look at the carboxylic acid here, and this carboxylic acid. They're both linear. granted. But there's another thing I want you to notice, and that is that they have even numbers of carbon atoms. Okay, now that turns out to be significant because of the biosynthesis. That tells you that these molecules, these linear carboxylic acids, are assembled from 2 carbon units. And so maybe later in the semester we'll talk about this, but there's a very well-studied biosynthetic mechanism that shows you how you take these 2 carbon units and you hook them together again and again and again, and then you get always even numbered carboxylic acids. So those are the common ones. So here, notice it's 26, here's 18, and those are both even numbers, obviously. So we don't need to talk about making soaps, but obviously if you take this stuff and you cook it up with potassium or sodium hydroxide, you get the sodium or potassium salts of those fatty acids, and those sodium or potassium salts of the fatty acids are soap. And why are they soap? Well, because they form micelles in aqueous solution. The micelle has a polar head group conferring water solubility. It has a lipophilic interior volume which dissolves grease and fat and dirt. The dirt dissolves in water. That way you can wash it off with a rinse. So this was an important chapter for us, and we've gone a little bit longer than we wanted to, but that's okay. And it was the chapter where we talked about the structure and reactivity of carbonyl derivatives. And so, and we talked, of course, about spectroscopy and a few other things. Now, the importance, of course, is not to memorize the melting points or boiling points or try to figure out exactly where the IR frequencies are. You can remember that, more power to you, but you don't need to know that. What you do need to know, however, are the mechanisms for reaction and, importantly, the reasons why things react the way they do. Why is that important? It's important because that allows you to make predictions. Okay? So you'll notice that throughout this course, 272 and 273, what we've emphasized are making predictions about reactivity. So at the end of, when it's all said and done, what you should be able to do, particularly for a biochem course, is to take a look at two reacting species and understand why they come together the way they do based on first principles. Okay? So let's talk about acid catalyzed hydrolysis of esters. I'm not going to go through all the mechanisms, but I think this one is one you probably can learn something from. So I have an ester, methyl ester. Do I care about what R is? Heck no, it can be anything, right? And so now I want to hydrolyze this using acid. And so aqueous acid, of course. And so if I show aqueous acid like so, then what's the first thing that's going to happen when I mix this stuff with aqueous acid? First thing that's going to happen is a reversible what? Acid-base reaction. No, it's okay. So that's going to happen reversibly. Now, why did I show protonation of the carbonyl oxygen and not the ester oxygen? Why did I show protonation taking place here? The reason is because this is resonance stabilized. And I'm not going to show you the resonance structure. You can figure that out. If protonation takes place here, guess what? The cation is not. So this is the nucleophilic oxygen atom, the basic oxygen atom. Okay? Okay, fine. So now I've activated this carbonyl group. When you activate the carbonyl group, what's going to happen? Well, there's lots of water around, right? Because we're doing this in excess water, so I'm going to get reversibly a nucleophilic addition to the carbonyl. And so this is the new bond I just made in that step from the nucleophilic addition of water. Okay, so I get to there. Now, from here, what happens? Well, you know what happens. Proton transfers always take place rapidly and with low activation barriers. There's lots of water around. And so water can pick off that proton, so to speak, like so, right? And I can get H3O plus. That's what happened to the water. That's what happened to this water. And I still have my tetrahedral intermediate, which now looks like this. This is the conjugate acid, that's the conjugate base. This is the conjugate base, that's the conjugate acid. So acid-base chemistry. Now, the next thing that happens is a lone pair here picks up a proton. And the next thing that's going to happen is I'm going to have a OCH3 plus right there. Okay, now at this point, I have a very good leaving group. This whole piece here is a good leaving group. Over here, it's not, because here it will leave as methanol, a neutral molecule. Here, it would have to leave as methoxide, a strong base, and therefore not a particularly good leaving group. So this is a better leaving group than that. And so what happens next is just what you expect. You end up losing the leaving group, forming methanol as one product, and forming the conjugate acid of the carboxylic acid. And I won't show loss of a proton from here, but you can easily imagine how that takes place. So this looks like just exactly the reverse reaction of something we've seen before. What? The Fischer esterification. So if you know Fischer esterification, if you learned that when we talked about it, then this is no different. This is exactly the same. It's just the equilibria are pushed in the other direction using what? Using the Chatelier's principle. So if we want to hydrolyze the acid, we use water, hydrolyzed water. If we want to esterify, then we have to remove the water from the equilibrium, so to push the equilibrium in the other direction. So this is the kind of mechanism that we need to remember and kind of understand. Most of the mechanisms that we're going to see, however, are going to depend on a two-step series of reactions that are typified here. Addition of a nucleophile to either a carbonyl or an activated carbonyl to form a tetrahedral intermediate, followed by collapse of the tetrahedral intermediate. They all follow the same principle. Okay? So, what did we talk about first thing today? We talked about methyl Grignard or methyl lithium addition to an ester. It's the same thing. Look, you had an ester. Here it is. I'll draw it again. So here's your ester. And then I had methyl ester, there you go. And then I had methyl Grignard, which I'm just going to abbreviate that as methyl minus. Nucleophile electrophilic carbon. Addition to form a tetrahedral intermediate. Okay, now let me alert you to one thing. I'm not showing an equilibrium here. This is not an equilibrium. This, on the other hand, is an equilibrium. I'm adding water to that activated carbonyl. Here, no equilibrium. Why? Well, because look, the difference is I formed a CC bond here. And that's going to be a very strong bond and a difficult one to break because why? To break that bond, go backwards, I have to generate a really, really, really strong base, not a leaving group. Methoxide, much weaker base than CH3 minus, and so I can split off methoxide, end up with a methyl ketone. Of course, if there's more methyl minus around, then it will react like so. And so these reactions, all of them follow exactly the same paradigm. Activation of the carbonyl in acid or not in base. Nucleophilic addition, you generate a tetrahedral intermediate, collapse of the tetrahedral intermediate. That's all you remember. You can figure out each and every one of these mechanisms. I think that's fair to say. Okay, we talked a little bit about reductions. And one of the things that you do need to remember is that there's a kind of a fundamental difference in the outcome of reduction using hydride of a ester and an amide. And so if I'm going to reduce an ester with lithium aluminum hydride, and by the way, you do need to use the reactive with LAH, won't go with sodium borohydride very fast at all. Then you end up with two pieces. You end up with a piece from the left, that's the black piece, that's the alcohol that you get from the carboxylic acid, and an alcohol derived from the right-hand piece, that's the red half. And so when you do reduce an ester, very often you have kind of a separation problem at the end, because if you're interested in one alcohol and not the other, then you got to separate the two. That can be a nuisance, by the way. So from a practical point of view, this is sometimes not a particularly good thing to do, but you need to know the mechanism. So that's what happens when you reduce an ester with LAH. Now, if you reduce an amide with LAH, then, and it doesn't matter whether it's a primary, secondary, tertiary amide, let's just show primary amide, then the CN bond is preserved in the product. So if this were an ester, you would cleave that bond and form two things. With the ester, the whole molecule is intact. So you only get one amine out of the reduction of an amide. You reduce an ester, you get two alcohols. You reduce an amide, you get one amine. You don't get two things, you get one amine. Now, the reason for this dichotomy in reaction outcomes has to do with the fact that you generate intermediates from this reaction that look like imines or iminium ions. And so go back and remind yourselves about what the difference is between an imine and an iminium ion. You get those from reaction of a primary or secondary amine with an aldehyde or a ketone. And then take a look at that mechanism, and it should make sense to you. It's not that different, but you need to remember that there is this dichotomy in outcomes of the two. The rest of what we've talked about is pretty well, we've gone through this today. So let's, coming up to the present, let's just remind ourselves of the reactivity series. I haven't shown anhydrides. Anhydrides are right here. They're a little bit less reactive than acid chloride. So it goes from acid chloride, anhydride, aldehyde ketone, then esters and acids, amides, and then finally nitriles. Don't memorize it, understand it. The reason for the reactivity can be easily understood if you just think about leaving groupability of what's attached to the carbonyl. So chloride is a really good leaving group. Acetate, if you have acetic anhydride, less good. Methoxide, less good. Amide, poor, very poor. And then nitriles are sort of in a category of their own because the carbon-nitrogen bond is a strong one. And so if you're going to do anything here, you have to disrupt the strong bond. So that's kind of the highlight of chapter 21. Chapter 21 and these chapters on carbonyl reactivity, I'll repeat myself, are really at the heart of organic chemistry. And so most of organic chemistry is really carbonyl chemistry. And so we're going to talk now in chapter 22 about reactions of enols and enolates. And the use really of carbonyl groups to make carbon-carbon bonds. And so the significance of carbonyl chemistry is that it provides you with a way of making carbon-carbon bonds. And as I've said many times before, the synthesis of carbon-carbon bonds is sort of what's really important in organic chemistry. So let's take a look here. And I alerted you to this reactivity recently, so let's go over it again. So we saw that if you have a carbon-oxygen double bond, you know that the oxygen is electronegative with respect to carbon. So that carbon-oxygen double bond is polarized. Negative end on oxygen, positive end on carbon. So the CO double bond, always think of the carbonyl carbon atom as having a partial positive charge. If it has a partial positive charge, then it's going to react with things that have a negative charge or partial negative charge. So all the reactivity can be understood on that basis. Now, it turns out there's another reactivity, however. So what I just told you about is this reactivity. This carbon has a partial positive charge. The other reactivity has to do with the fact that the hydrogen, this one here, is acidic. And it's acidic because when I pull it off with a strong base, I end up with a resonance stabilized species called an enolate. And so I've shown only one resonance structure here, but you can generate the other one. I've shown the important resonance structure. Enolates are nucleophiles. So this is an electrophilic carbon atom. The alpha carbon is a nucleophile. Now that is very powerful because it gives you two kinds of sort of complementary reactions that any carbonyl compound can undergo, provided that carbonyl compound has at least one alpha carbon atom. Obviously, if this is a carbon and that's a carbon, no way to get an enolate, right? You've got to pull a proton off of here in order to get an enolate. And so this carbon is a nucleophile, this one's an electrophile. Electrophile, nucleophile. Okay. So an enol, which we've seen before, we saw enols actually in Chem 272 in the context of what? Of acid-catalyzed hydration of alkynes. And remember that when we took an alkyne, we added aqueous acid, usually with mercury catalysis, we ended up with a ketone. The mechanism went through an enol. So go back, take a look at that mechanism. It's one of the early mechanisms that we discussed in this class. It's fairly complicated. Go take a look at it. It should make sense to you and refresh your memories. Now, the enol is the conjugate acid. The enolate, 8 always means negative charge, is the conjugate base. Which of these two is a better nucleophile on the carbon? Well, the negatively charged one, for reasons that we've talked about when we talked about SN2 chemistry. Remember when we talked about substitution chemistry? What did we say about nucleophiles? We said that if you had a nucleophile, if you had two nucleophiles, same nucleophilic atoms, carbon, we're talking about carbon and carbon, oxygen, oxygen, and so on. One of them has a charge, one does not. Then the one that is charged is going to be the stronger nucleophile. The one that is uncharged will be a less reactive nucleophile. So, reactive, less reactive. Now, the other part of the chapter is alpha beta unsaturated carbonyl compounds. So let's take a look at one of these. Let's take cyclohexenone as alpha beta unsaturation. Now, why alpha beta? Well, because there's the alpha carbon, that's the beta carbon. I can draw these three resonance structures for cyclohexenone. And one thing you should notice is that the beta carbon atom is a partial positive charge. So what this tells you, and we're going to see this, is that when you have alpha beta unsaturated carbonyls, the nucleophile, nucleophile as the carbonyl, yeah, you can add to the carbonyl for sure. So if I have a nucleophile add to the carbonyl, there's a partial positive charge there. But guess what? You can also add there. And so I have two sites where nucleophiles can attack. You can either attack here or there. And depending on conditions, you'll get one kind of product or the other. Okay, so now all of a sudden things got complicated because I look at alpha beta unsaturated ketones, just take a look at that one. And all of a sudden, just based on what I told you this morning, you say, oh, but how do I know which way it's going to react? It can react in any number of ways, right? So you can say that, well, if I have a nucleophile, it can react at that carbon atom. Or if I have a nucleophile, it can react at that carbon. Or if I have a base, it can form this enolate. I'll just show the enolate here so you can see it. But if I have a base, it can also react here, can't it? And so base can react like so to form this enolate. And so all of a sudden, I've got four different kinds of reactivity based on first principles. Which one takes place is something that actually we can make very good predictions based on first principles. And you're going to see how we do that. But this tells you that even with a really simple molecule, it doesn't get much simpler than that, all of a sudden, complexity. Complexity because it can go four different ways. And so this turns out to be one of the reasons why you can form so many different kinds of structures starting from simple organic molecules. Sometimes you have multiple ways in which things can react. Okay, now let's talk about the formation of enolates. Enolates are going to turn out to be important. So let's take this ketone. This is acetophenone. And, you know, these protons are not all that acidic. My gosh, you know, the pKa of this stuff is around 18.2. Is that a strong acid? Heck no. I mean, that's a really, really weak acid. And so what that tells you is that if I want to form the enolate, what do I have to do? I've got to treat it with a really, really strong base. Now, yeah, I've got to treat it with a strong base to pull off that proton because, yeah, the pKa is really high. But that base has to have another property, and this is something to keep in mind. That base had better not be nucleophilic. So I need something that is a strong base, but it also has to be non-nucleophilic. Why do I care? Why does the base have to be non-nucleophilic? I mean, I can understand strong, but why non-nucleophilic? Well, for ketones, maybe it doesn't make as much difference, but for esters, which are even harder to deprotonate because the acidity here is even lower, this base had better not be a good nucleophile. Why is that? We talked about it this morning. Well, what the nucleophiles do with esters? They attack the carbonyl, right? So I have two different kinds of reactivity. Remember, I have acidity of the alpha carbon, but I have also electrophilic activity right there. So if I'm going to treat this, either one of these, with a base that is also a good nucleophile, then I have a competition. I have a competition because why? Well, because instead of pulling the proton, it might just form the tetrahedral intermediate. And so I've got to suppress that nucleophilic activity or I don't get the enolate. It makes sense, right? So what's a strong base? What are the strong bases that we talked about? Well, the strong bases that we've talked about are amides, RNH2 minus, right? So we talked about sodium amide, NaNH2. Remember that? We talked about that as being a strong base. Think of this as Na plus NH2 minus, so it makes sense to you. So we talked about that being a very strong base, but deprotonating what? We're deprotonating alkynes. That's when we talked about it. Is this a non-nuclear? It's a strong base. Got it. Is it a non-nucleophilic strong base? No, this is a good nucleophile too, because the hydrogens are tiny. So this tells you what you need to do. What do you need to do to convert NaNH2, strong base, good nucleophile, to something that is strong base, lousy nucleophile? Yeah, you can't have hydrogens here. So one of the ones that's used is disopropyl amide. So this stuff here, in fact, lithium disopropyl amide, is used so often it has its own acronym. It's called LDA. Okay, so LDA is often the base of choice. Strong base because N minus, non-nucleophilic. Why non-nucleophilic? Well, because isopropyls are big. Okay, and so that's how you get around this problem. Okay, so this just, whatever base we choose must be non-nucleophilic, and the reason is so that it pulls a proton and doesn't add to the carbonyl. How do you do that? Use LDA. But LDA is not the only one. There are, I don't know, dozens of these things, but that's the common one. The reason it's common is because disopropyl means cheap. So there are other ones that work. Okay, so here's one that's not so cheap. That's a much stronger base. And okay, so think of that one, right? Because now you have not isopropyls, the tertiary carbons. And this is a completely non-nucleophilic nitrogen atom. This is actually a strong enough base to pull a proton off a benzene ring. Think of that. And it was developed for that. We'll talk about that reactivity maybe later on. Okay, now, the negative charge of the enolate, yeah, I didn't make a big deal of this, but you should know from writing the resonance structures that negative charge is distributed between the oxygen of the enolate and the carbon of the enolate. Okay, it's like an allylic anion. It is an allylic anion. And so when we drew allylic resonances for allylic anions, we have carbon and carbon. But here we have carbon, oxygen. So this is, you can think of this as being a allylic with a negative charge on carbon. This is a allylic with a negative charge on oxygen. What's more electronegative, carbon or oxygen? This one, oxygen. So that's the important resonance contributor. On the other hand, so you say, well, if this is the important resonance contributor, then whenever you form an enolate, any kind of reaction should take place on oxygen. And that's not true. That is fairly confusing. And it doesn't have a simple explanation. We may talk about that, but very often you get C reactions on the carbon, not the oxygen. Okay, now, so this is how you form an enolate. Now we're going to have to ask ourselves a question. The question is this: what happens to the acidity of the alpha carbons in the following example? In other words, is this more acidic, less acidic than this stuff here, and why? So if I try to form the enolate here, can I do it, and why can't I? Why is that going to be a really, really lousy enolate to form? Well, why was the acetophenone one easy? The acetophenone one is easy because why? Because the enolate is resonance stabilized. So now the question is, well, you know, why isn't this resonance stabilized? Well, let's take a look. So let's go over here and take a look. So let's just say that I pull that proton off. Imagine a base, LDA, whatever, coming in, pulling that proton off, okay? So the first thing I did is this, right? Now the question is this am I within my constitutional rights drawing this kind of enolate?
Red's rule violation.
Yeah, because it's Red's rule. So you guys know. Now, what that tells you is that the reason, by the way, the reason this is not resonance stable, the reason this has no validity is because there's no way to form that pi bond. Why is there no way to form that pi bond? Well, because you have to think of the orbitals. The 2p orbital here and the 2p orbital there are at essentially 90-degree angles. No overlap at all. Because there's no overlap, then I can't really say that there's a pi bond there. And so, this is not going to give rise to a resonance-stabilized enolate. However, there is one other feature that will stabilize that anion. That's a polar effect. We didn't talk about that, so now's the time. So, when you form an enolate, yes, it is resonance-stabilized. I mean, this one is. But there's also something else going on. That is that you have a favorable charge dipole interaction. In other words, the proton, this particular one, is rendered acidic because that carbon atom has a delta plus. Okay, so that means that this anion is stabilized by the adjacent positive charge. And so that stabilization doesn't go away just because of Red's rule. And so this is still going to be a bit more acidic than the protons, say, so this is going to be more acidic because of that than, say, this one here, and the protons on this side. But that is not a huge effect. Now, you can see that the big difference between an allylic carbanion and an enolate. That's an absolutely astronomical difference in acidity. And they're both resonance stabilized, but of course this one has this favorable charge dipole interaction and the electronegative oxygen atom. So yes, they're both allylic, but no, they're not the same because oxygen is not carbon. Oxygen is electronegative. And because the enolate, a negative charge would sit on the electronegative oxygen atom in the dominant resonance form, much easier to form an enolate than to form an allylic carbanion, okay, by deprotonation. Okay, so now we try to understand why ketones and aldehydes are so much more acidic than esters. Okay, so I didn't really point to the numbers, but you know, if you look at the numbers here, pKa's, that's 10 to the 7th difference. That's 10 million times difference. So this is 10 million times less acidic than that. How come? Well, the easy answer, the short answer, is because the ester is not the enolate. The ester is resonance stabilized to a much greater degree than the ketone. The enolate of the ester and the enolate of the ketone are resonance stabilized to almost the same degree. And so remember, when you compare things, you've got to make sure that you're comparing properly. So if I say that, well, so imagine the ester and the ketone. You say that, well, you know, the ester is more stable than the ketone, and that's why. That doesn't hold together logically, because I could have, say, a situation like this where I have ester. So this is down here, and ketone is up here. But if the distance to enolate is the same, then, you know, if this distance in energy increases this way. So if the distance in energy between ester and ketone is the same as enolate and enolate, then it's a wash, right? And so I have to be careful to compare the stabilities of the ester and the ketone, but also the enolate derived from each. So an energy diagram actually makes this fairly clear. This is what's going on. We'll come back to why. The ester enolate is lower. The ester, pardon me, is resonance stabilized compared to the ketone, but the enolates are about the same, and so it's much easier then, smaller activation energy, to go from here to there. I don't have to go over such a big amount. But here, energy difference is substantial, right? Okay, so let's take a look and see why that should be. So let's write the resonance structures for the ester. So I have these three resonance structures for the ester, and these two for the ketone. So the ester has an additional resonance structure that the ketone doesn't. Okay, so this one corresponds to that, this one corresponds to that, but there's nothing like this for the ketone. Ester has an additional resonance form. The ester is a little more stable. But what about their respective enolates? So now look at the enolates. Well, the ester has enolate has three resonance forms, and the ketone only has two. But this resonance form doesn't count. We don't have to worry about this one, because here I have a huge amount of charge separation, and worse yet, two negative charges fairly close. And so remember when we were drawing resonance structures, we said something about how to determine relative energies, and that by determining the relative energies, you could determine which resonance structures were important, which ones you just didn't have to worry about. Well, the ones that have a lot of charge separation or multiple charges, those are going to be much less important than ones where you don't have that. So this kind of a resonance structure, not important. Not important because instead of having one negative charge, it's got two negatives and a positive. Lots of charge separation plus negative charges too close. So I don't have to worry about that. So essentially, ketone enolate, ester enolate have same number of resonance forms, same amount of stabilization. Okay, so bottom line, making ketone enolates or aldehyde enolates really easy. Making ester enolates much harder. Okay, now there's another property of enolates that we didn't talk about, and the reason we didn't talk about it was because the examples I showed were all fairly simple. So let me take just kind of a walk back in time. Okay, if I have a sp3 hybridized carbon atom like this, R1 or 2 or 3 or 4, whether none of them are the same, then this carbon atom, without even having to think about it, is chiral, right? Okay, so just remember that. Now, I can do the same thing, and I can show you what the R1s are. Okay, so now the R1s are as I've shown here. So R1 is phenyl, R2 is hydrogen, benzyl, and benzoyl. And so this is a chiral compound. And so if it's a chiral compound, it has two mirror images, each of which are non-superimposable. Okay. So let's just say that I have one enantiomer of this chiral compound. So I have one mirror image form, okay, the one I've shown you. And I treat this with butoxide and butanol, strong base. There's a fast reaction that immediately gives me the racemate. Okay, so I end up taking this compound, which was one enantiomer, treat it with base for a short amount of time, and all of a sudden, any optical activity associated with that goes to zero. I have a racemate. Why is that? Well, you kind of know already, because these are conditions that are going to generate the enolate. And so the first thing that's going to happen here is I'm going to pull that proton with this alkoxide to form an enolate. Now, I've shown the enolate in its important resonance form. The important resonance form is the one that places the negative charge on the electronegative oxygen atom. That's why I'm showing that. Notice that that resonance structure is also planar, which means it's achiral. So once I pull that proton off, I lose stereochemical information at that carbon atom. This is planar, I'm showing it here like so. Now, when this thing gets reprotonated by butanol, it can either follow a green pathway or it can follow a red pathway. Green pathway means the proton comes from the top face, red from the bottom. And that generates two different stereoisomers. In fact, it generates each of the two enantiomers. And so it's very easy to take a chiral ketone, chiral aldehyde, chiral ester, whatever, and racemize it. This is usually the reaction you don't want to have happen. Okay? Usually, you've gone through a fair amount of trouble to generate a single enantiomer. Getting a racemization reaction most often is not what you want. It's easy to do because once you pull that proton, this is planar and you lose the stereochemical information. Now, there are a few exceptions, and they're not really exceptions to the rule. There's some very surprising reactions where you can take alpha chiral carbonyls, pull the proton off, and not lose stereochemical information. I'm not going to tell you how those work. Maybe I'll ask you to think about it on the exam. I don't know, maybe. But I won't. Somehow I don't see the humor in that, do they? Is it fluorine in the morning or what? Or the humor of the challenge? Okay, so the reason we get racemization, of course, because there's equal probability of protonation taking place from the top and the bottom. What does that mean? It means that the two transition states for protonation from the top phase or protonation from the bottom phase, those two transition states are enantiomeric. They have identical energies. They have identical energies. They're formed at identical rates. And so once that thing goes planar, you've lost it. You get both enantiomers. Okay, now we get to the real thing here. So we said that nucleophiles are that enolates are nucleophilic, and they're nucleophilic on carbon. They are also nucleophilic on oxygen, and there are ways to control whether you get nucleophilicity on oxygen or on carbon. That's probably a little beyond what we need to talk about today, but they are carbon nucleophiles. And so if I have a nucleophile here and an electrophile there, I get an SN2 reaction. This is an alpha alkylation reaction. This is a very important process. Okay? And so you don't need necessarily an alkyl iodide. Other leaving groups on carbon will work. But this is the kind of reaction that forms a carbon-carbon bond. Now, because the enolate is nucleophilic, I can allow that to react with carbonyl. Remember, the carbonyls are electrophilic. And so I end up forming a carbon-carbon bond, that red one, by allowing a nucleophile to react with an electrophile. This is not an SN2 reaction. This is something we've not seen before. But this reaction is an SN2 reaction. It's the same thing we talked about in Chem 272. Now, here again, you can see how complexity is built up, right? you go back to that example I talked to you about a little while ago, where I talked about all the different kinds of reactivity that you can see with cyclohexenone. Now you can see that the enolate, either this enolate or that enolate, can react with the starting material. Because this is a nucleophile, this is a nucleophile, that's an electrophile. And so all of a sudden, you can see how combining a ketone with an enolate can give rise to lots and lots of new compounds. And that turns out to be a key reaction in biochemistry, as well as organic synthesis. So we'll stop here, we'll pick up on Wednesday.